Welcome back. Now we have Lindsay Homewood, who is here to tell us how to make users of your cryptographic library successful. Lindsay is a product and engineering manager working at CipherStash as the lead or their chief product officer. Previously served as the head of technology at the Australian Federal Government's Digital Transformation Agency. He also won third prize at the 1996 Sydney Royal Easter Show Lego building competition. Lindsay will endeavour to allow time at the end of his presentation for questions. So please leave your questions in the question tab. Over to you, Lindsay.
Great. Thank you so much, Greg, for that lovely introduction. And just a big shout out and thank you to all of the organisers as well who have been involved in putting this production on. It's pretty amazing to watch behind the scenes, how much effort and hard work they're putting in to create an experience like this. So big hat tip to all of you. So my name is Lindsay Homewood. I am the Chief Product Officer at CipherStash, where we are trying to build a new searchable encryption technology, commercializing that. And so a big part of my job is focused on how do we actually make the cryptography technology that we're building usable by our users. And in a product role, typically you can go out and you can do, in a maybe a less technology-focused company, you can do a lot of interviews with users, but it's a bit of a different set of challenges, I guess, when it comes to working with developers and looking at how they're writing code and how they're using the code that we're writing and shipping to our users. So I spend a lot of time looking at academic research about cryptography usability overall, and fortunately this intersects really well with open source because pretty much all of the research that we've had into cryptography, the security and the usability side of it is based around open source technologies. So I've read probably close to 50 papers in the last couple of months about open source cryptography and the usability of that. And what I'm going to be doing today is sort of stepping you through sort of the highlights and the lowlights of it. And in case you're wondering about what the hell a footgun is, it's sort of like an old Unix sort of programmer joke of it's a feature that is likely to shoot users in the foot, which obviously we don't want to do when we're doing cryptography and helping people be successful with the libraries that we're building. But before I start, I would like to acknowledge the traditional owners and custodians of country throughout Australia, which in my case is the Darkinjung people, and recognise their continuing connection to land, waters and culture. We pay our respects to their elders, past and present. Sovereignty has never been ceded and treaties have never been signed. It always was and always will be Aboriginal land. So cast your mind back to 2020. You might not want to because things have not been great since 2020, but let's talk about something particularly dark that happened in 2020 that you might not be aware of. If you thought it was bad already, just wait till you hear about this. So there was a health tech startup in Finland named Vastamo that suffered a fairly significant data breach. So they had over 300,000 patient records leaks, and those were including detailed consult notes written by a psychologist or psychiatrist during a session with a patient. And this information was leaked on the internet and actually used to extort patients of this particular service. So this had a really tangible human impact on the people that were involved in this data breach. So this particular person, from this article, I highly recommend you give it a read, from William Ralston in Wired. This particular person got a message on Snapchat saying, hey, your data is in this massive breach. And this is from when he used Vastamo's services a couple of years prior, but hadn't been using it. So these are people that have had significant trauma in their life and significant mental health issues, and this information was just leaked right out there. And the people that did this took it one step further. They actually were blackmailing people and saying, "Hey, you need to pay us a bit of Bitcoin for us to permanently delete this information in the data breach that we've just done." So a pretty bad situation overall. And when the researchers and the incident responders dug into it afterwards, there was a pretty glaring flaw in their entire system, which is that it didn't encrypt any of the data at all. In fact, it was just a plain old, I believe it was a MySQL database with a PHP-based web app. And yeah, just some very basic network access controls, but there was no encryption in the mix in any of this. And you're probably thinking now, wow, that's pretty messed up. But I would never do this because I am smart and intelligent, and I am at a conference like this, like LCA, and taking time out of my weekend. And I would never, if I was put in a position to build and design a system such as this, I would never build it in this way that I wouldn't use any encryption. And the problem with this is it doesn't really matter what your intentions are. In this particular study, which we're going to talk about a little bit later, that was comparing the usability of different cryptographic APIs. The researchers found that in these programming exercises where they had people writing Python to encrypt and manage data, they found that 20% of the submitted code was insecure, but it was even worse than that because the developers who submitted that code strongly believed that that code itself was secure. So it may not matter that you might say to yourself, I would never do this. The fact of the matter is that the way that we build cryptography tools and cryptography libraries directly impacts the security outcomes for our users or the developers and also their end users as well. And I think Mark Twain sort of said it best where he said, it ain't what you don't know that gets you into trouble, it's what you know for sure that just ain't so. So you might be super confident about this, but it doesn't necessarily even matter. And the great news for us is that there is this burgeoning field in the humanities. It sort of lives at the intersection, actually, of comp sci and humanities called human factors and secure software development. And there's been this massive explosion of research over the last sort of 10, 15 years in particular. But I've seen, in looking at all these papers, I've seen at least 3 doctoral dissertations in the last 6 months for people that are trying to acquire their PhD in human factors and secure software development. So there's a rich vein, a rich resource that we can tap into here to learn what the problems actually are and how we can not make those mistakes and only make new mistakes. So what we're really going to do is we're going to look at the usability traps in the cryptography libraries, some of which you may be familiar with, others you may not be, and the sort of things that you can do to help your users avoid them. And before we begin, just a quick note, we are talking about cryptography, not cryptocurrency. We don't serve any of their kind here. And we're talking specifically about developers, where when we say the users of a particular piece of software, we're talking about those being developers, not the actual end users who may be using a high-level application to be able to store their data and perform a particular task. The last thing as well to note is that we're looking at peer-reviewed research. Much of it has been replicated as well, and I've got an extensive list of sources at the end that you can go and have a look at yourself if you want to dig into the details. Really thorough, complicated, interesting work, and if you've got some time, you're looking for some light reading on a Sunday afternoon, I highly recommend a lot of the papers that we're going to be talking about today. So I want to start with a base level fact, which probably makes a few of you uncomfortable. In fact, I'm probably not talking to the people that are in the audience here today, because if you care about security, you're probably at this talk. But on the whole, developers pretty clearly don't really think about security at all. So there's this fantastic paper published in 2014 called It's the Psychology Stupid, How Heuristics Explain Software Vulnerabilities and How Priming Can Illuminate Developer Blind Spots. And this research is led by Daniela Oliveira. And this is a really interesting experiment. We're going to sort of rapid fire through a bunch of different papers here today. So in this particular experiment, what they did was that they showed developers 6 different code examples that contained vulnerabilities. So the typical sort of things that you're probably familiar with, like buffer overflows, TLS setup, cross-site scripting, TOC2, time of check to time of use, SQL injection, and brute force exhaustion. So what they did was they showed these insecure code examples to participants in this particular study who were developers. And so the developers in this particular study were grouped into 3 different cohorts. So there was control, there was a priming cohort, and there was an explicit cohort. And so in the control cohort, they were asked, what is the user input to this program, and what happens when this code executes? In the priming cohort, they asked those same 2 questions, but then they layered 2 additional questions on top of that. They said, could a developer experience unexpected results when they run such code? And what could examples of these unexpected results be, and where do they appear in the code? And then in this 3rd cohort, where they were explicit, they just said straight up, this code has a vulnerability. Can you pinpoint the problem? And the results of this were that the developers who were primed about there potentially being a security problem here identified security problems at almost twice the rate of unprimed developers. So one of the things that they say in this paper is that security is not really part of the heuristic used by developers in their daily programming tasks. And that's because developers on the whole are focused mostly on functionality and performance. Can I get this code to run to meet a particular business or organizational objective? And does it do it relatively quickly? Right? Those are the top two things that developers are actually focused on when they're writing code on a day-to-day basis. And the mental model that we have when it comes to security education is that we think that developers should learn about security. So often that's taking time out of their day to go and learn that, or maybe if they're going through an education institution, that's part of the coursework that they are doing. And so they should just go and learn that, and then they should apply what they learn when they need it. And the fundamental reality here is that this is not actually how humans actually think. We're great at acquiring a whole bunch of different knowledge, but there are very specific triggers that are required for actually having us apply that knowledge at any particular point in time. So they make this really strong recommendation that software that interfaces with the developers, so that's like IDEs, text editors, compilers, static analysis tools, that those tools prime developers on the spot when they need it, while they are actually coding. So when they are cutting the code in their text editor and then running it, that's when we should be providing feedback to users about their code potentially being insecure, or actually telling them, hey, it's actually quite insecure the way that you're using this right now. So the TLDR for this particular paper is the devs don't really think about security, but priming significantly increases the likelihood of discovering security bugs. So another potentially uncomfortable truth, something that you may know but you really wish you didn't know, is that Stack Overflow provides functional yet insecure code examples to developers. And so there's this fantastic piece of research that was published in 2016 by Yasmin Acar, Michael Bucks, and Sasha Fal, called "You Get Where You're Looking For: The Impact of Information Sources on Code Security." And in fact, this particular group of researchers, they sort of have a nice sort of narrative thread throughout everything that we're going to be talking today. This particular group, based over in Germany, a bunch of educational institutions over there, have done some pretty phenomenal work on the human factors in secure software development over the last sort of 5 to 10 years. And so in this particular experiment that they constructed back in 2016, what they did was that they recruited Android developers through GitHub and a variety of other sources, and they provided those Android developers with a skeleton app. And they were also presented with 4 tasks in a random order here. So it was a combination of secure networking, secure storage, intercomponent communication, and least permissions. And so the developers were time-boxed to 20 to 30 minutes per task. And then at the end of that, they were asked to fill out an exit survey about how they felt they performed and whether their code was secure. And so the Android devs that will run through this process was split into 4 separate groups. So the first group, they could only refer to information on Stack Overflow. The second group could only refer to information in the official documentation. The third group could only look at books. And the fourth group could look at any of these information sources. And the books weren't hard copy, they were actually a digital copy of the book, so they could use the table of contents, they could use like the find functionality in their PDF viewer. But yeah, so it wasn't entirely Stone Age, but it's a relatively comparable sort of technological means to be able to access this information. But that information itself, what sources they could use, was significantly restricted. And the results? Well, the results sort of fall into 2 separate buckets. So there's the functional results, where they're able to deliver code that was functional and did what it was intended to do. And the second part was, what is the overall security of those particular results? So let's look at the functional first. And so in the functional, they found that Stack Overflow, people who use Stack Overflow, had a significantly higher success rate. In fact, Stack Overflow and books, funnily enough, had a significantly higher success rate than people that were using only the official documentation or the people who were doing free choice. In fact, it's so bad that the devs that were assigned the official documentation actually performed the worst overall, which is sort of a bit of a damning indictment, I guess, of a lot of official documentation, particularly when it comes to cryptography. So that's on the functional side, but the security side of things was really interesting. So they found that with the least permissions, with about 87% success rate, that was the highest out of all of them. Everything else is about the same, about sort of 38 to 40%. So for the secure networking, the intercomponent comms, and secure storage, it was very, very low success rate, but the confidence was super high, even though they were actually not producing something that was actually secure. So on the whole, developers self-assessed their solutions to be secure when they mostly were not. And what that means for us as developers is that in this particular study, Android developers who use Stack Overflow, they do get functional code quicker, but are more likely to produce insecure code. Sit with that for a second. Like that's pretty wild when you think about it. And when we think about, the previous study we talked about a moment ago, where, we look at priming and heuristics and whatnot, developers are mostly focusing on functionality and performance. So, of course, they are going to continue to go to Stack Overflow because it produces functional code. It helps them actually meet their objectives, the things that they are often incentivized on within their organizations, mostly functionality and performance. So they have a pretty strong recommendation that it's really critical for people who build cryptographic libraries, particularly in the open source space, to develop documentation and resources that combine the usefulness of forums like Stack Overflow, so sort of a Q&A type situation or like a forum, but with the security awareness of books or the official API documentation. So one really interesting thing that you can do if you're a maintainer of an open source cryptographic tool is that you regularly spend time looking back at yourself on Stack Overflow, looking at the questions that your users are asking on Stack Overflow about your library or about your tool. Use that as a way to identify gaps in your documentation that are being filled by Stack Overflow, and then fill those gaps in your own official documentation. Because we're going to talk about this in a second, actually, with some of the other research, but typically the official documentation tends to have the most secure results for developers. And so the last thing to do here is to post links and follow-up comments on the accepted Stack Overflow answers back to your official documentation. And then over time, if you're looking at website analytics for your documentation, you should see an increasing number of people going to these pages, and you should see your official documentation ranking higher in Google. So the TLDR for this particular study is that Stack Overflow answers, they provide functional, insecure, but yet insecure code to developers. And developers are also really bad at assessing whether that code is secure as well. Quick side quest for a second though, there's this other paper that was published only a couple of months ago, back in November of 2021, about the effect of Google search on software security. So security interventions and doing content re-ranking, particularly for results showing Stack Overflow. And so I'll skip over a lot of the detail of the study, but they basically found that there is at least a 22.8% chance that 1 out of the top 3 Google search results for Stack Overflow leads to insecure code. Again, that's another damning statistic right there. So TLDR, insecure code ends up in the top results and is also clicked on more often. There's a higher engagement with it. So the study that they did for this was really interesting. So they used like the Google custom search engine functionality to boost or unboost different bits of content. And they asked the participants to perform Google searches using this custom search engine that was built into the survey tool that the users were going, or the developers were going through during this particular exercise. And they found that the participants that used the modified search engine to look for help online submitted more secure and more functional results with a significant statistical significance. So the TLDR for that particular paper is this is a fairly novel solution to the problem that actually requires zero behavioral change from developers. And my question is, if there is anybody that is listening to this talk today that works at Google, can you please go and I'll provide a link to this particular paper at the end, because I don't know how much traction it's really gotten outside of academic circles, but I guarantee there is some product manager or team within Google that could actually do something about this, and it would have an outsized effect on the overall security of code that the developers are shipping on a day-to-day basis. Really, really novel solution to this problem, and I would love to see it implemented, particularly within Google. All right, so the other sort of hard to hear, hard to listen to truth is that most what we call cryptography bugs actually come from the use of the libraries, not the actual libraries themselves. And so this particular study, published in 2014, called "Why Does Cryptographic Software Fail? A Case Study in Open Problems." They go into a whole bunch of different areas in this paper. They cover sort of 3 or 4 different topics, and we're just going to talk about one of them today, which is this this particular part of the study. So what they did was they did an analysis of 269 CVEs that were assessed as having cryptographic issues, which is from the Common Weakness Enumeration from MITRE. And they looked at that from January 2011 to 2014. And that's it. This is the foundational paper. There are other papers more recently that have replicated this, but this sort of articulates it pretty clearly. It was the sort of first movers in this field. And what they did was that they categorized the vulnerabilities for cryptographic issues as along 2 different dimensions. One was impact, so whether it was a plain text disclosure, a manipulator in the middle, a brute force, or a side channel attack. And then also at the layer as well. So was it at a low-level cryptographic primitive like AES or Diffie-Hellman? Was it at the protocol level? So that could be some sort of library or abstraction that bundles up a bunch of cryptographic primitives to be able to provide an actual usable interface to the developers that needed to access these primitives. And the last layer was the application itself. So, issues particularly like with plain text disclosure outside of the actual cryptographic libraries themselves. And the result of this was that 100% of plain text disclosures of information, 86% of manipulator in the middle attacks, and 79% of brute force were in the app layer. Now that said, 0% of side channel happened at the primitive and protocol layer, but that's the sort of problem that you would expect to be manifesting at that layer, right? But 100% of plain text disclosures were actually happening in the application layer. And that mostly came down to the way that the developers that were using these libraries were actually invoking them, what the ergonomics of the APIs were that these libraries were exposing. And so what you can do as a cryptographic library author or maintainer is that you can try and expose interfaces in your libraries that are what the academic circles term as misuse resistant. And that's really what the majority of the remainder of this talk is going to focus on. How do we actually achieve misuse resistance? And there's heaps of research into this, but there are fairly sparse actual directives as to how to actually achieve this. So yeah, what that fundamentally means is that about 83% of all cryptographic bugs come from the improper use of cryptographic libraries, not actually due to cryptographic flaws inside those libraries themselves, which again, another pretty damning statistic. So let's actually look at what you need to do to improve the misuse resistance of your libraries and the tools that you're shipping to developers. And the TLDR, probably like the number one thing that you can take away from this talk today is that the features on the periphery of your library, and I'll talk about what that means in a second, and the documentation that you ship with your library are the absolute number one requirement for developers to use your library securely. If you don't have an extensive range of features, an extensive range of examples and recipes about how to use it, and extensive documentation explaining all the different ways that you can use that library, you are doing a disservice to your users. And so this particular paper published in 2017, like I was originally just going to do a talk exclusively about this paper. I could talk about this paper hours. It's a brilliant read. It's super technical, but it's also it's very readable at the same time. And so this is by that same group of researchers that I referred to previously. So Yasmin Acar, Michael Bucks, and Sasha Fahn, and Simon Garfinkel. And it's called Comparing the Usability of Cryptographic APIs. And this has been cited heaps of times in the last 5 years. And I highly recommend, if you're going to read any paper out of the stuff that I'm talking about today, go and have a read of this. And I'll provide some links at the end as well. So this particular experiment was really interestingly constructed. So what they did was they recruited a bunch of Python developers, and they assigned those Python developers 5 tasks with a bunch of stub code. So those tasks were broken into 2 categories, symmetric and asymmetric. So for symmetric, it was key generation and encryption and decryption. For the asymmetric, it was key generation, encryption and decryption, and certificate validation. And at the end, they also asked the same sort of questions. Is the code that you're actually producing here secure? And they used a bunch of very common, well-known cryptography libraries that if you are a developer in the Python ecosystem, chances are you've used one of these libraries. So they were assigned libraries, one of these 5, so Cryptography.io, Kezar, Pinnacle, sounds like pineapple, doesn't it? Pinnacle, M2 Crypto, and PyCrypto. And they were instructed specifically to only use the included docs from these different libraries. Now, you notice the little sort of asterisk that I've got listed there. The top 3 libraries that I mentioned here are ones that make explicit claims about the usability focus for actually building those APIs. And so trying to build a more usable, misuse-resistant style encryption. It's also probably, if you're familiar with the space as well, it's worth noting that Kezar was deprecated in favor of Tink by Google in 2019 as well. So there's a whole bunch of things that were fed into Kezar, but I actually haven't seen this research replicated with Tink. So if anybody is looking for a little research project and you work in an academic institution, this would definitely be one to take a look at with Tink. And the experiment that they constructed was really interesting. So what they did was they modified a Jupyter Notebook and included the stub code in here for each of these tasks that I mentioned in the previous slide. And one of the other things that they did inside the Jupyter Notebook was that they would regularly take snapshots of the code, and they also detected copy and paste events as well to see where people were actually copying code from elsewhere on the internet, so they could trace it back to the original source, whether they were actually only getting it from the official documentation like they were asked to, or whether they were really actually going on to Stack Overflow. And again, the results are sort of in 2 separate buckets here, the functional results and the secure results. And not to give too much of a spoiler, but there's a similar discrepancy between the previous research that we were looking at and this particular paper here. So the functional results found that there was a wide variation of task success across different libraries. On the whole, asymmetric tasks were less successful, and they offer some discussion in the paper about why that might be. I think the general sense of it is that asymmetric encryption is just generally less well understood, and thus people are more likely to make mistakes with it. But, functional solutions, if you look at the symmetric tasks for Pinnacle down there, very, very high. Well, I mean, not perfect, but greater than 80%. So 3 out of the 5 had a functional solutions. 50. Greater than 80% of the tasks had a functional solution. You'll notice Kezar there, though, as we mentioned before, it was one of those libraries that made explicit claims about the usability. Not good. Like 40% of tasks, less than 40% of tasks had an actual functional solution. And don't worry, it gets even worse when you actually look at the secure results. But fun little anecdote from the Jupyter Notebook little thing that they slipped in before, they actually found that copy-paste code that they were able to trace back to Stack Overflow was 3 times more likely to be functional on symmetric tasks. So developers love copy-pasting. So if they're going to be copy-pasting code, at least give them functional and secure code to be copy-pasting. The other interesting thing that they found as well, they did an over-analysis of all the different results posted here. And they found the Python experience, the security background, and the library experience actually did not change the success rate of these particular functional tasks. So it doesn't really matter if you're a super experienced Python dev, have got a strong background in security, or heaps of library experience. You perform just as poorly as somebody that doesn't have any of that experience at all, which is quite a humbling thing to hear. And then we get into the secure results, and it's an absolute bloodbath. So in this particular case, although the functional asymmetric tasks are very, very low, they were 3 times more likely to actually produce a secure result. Kezar stands out amazingly here. You compare it to this one, right, where you see the functional results of Kezar being very, very low. But for the people that managed to do it, they had super secure results, which is curious, not good, I would say. So yeah, on the whole, the Quasar usage was 25 times more likely to be secure than any other library that was used, but only 10% of the submitted Quasar solutions were actually functional. Which, yeah, this is the sort of thing that I cry into my pillow at night about. It's not good, not good. And as I mentioned at the top of the talk, 20% of the submitted code was insecure, but the developers strongly believed that it actually was secure. So a bit of Dunning-Kruger going on here. The less you know about something, the more confident you are, and the greater you assess your competence at compared to people who do know something about it, which is, pretty sad. So what this actually means for us, though, as tool authors and library authors, is that libraries with simplified interfaces actually produce more secure results. So misuse resistance is good for security outcomes for our users. And yet, security success rate was less than 80%, even on the simplified libraries. So not great overall. One of the things that they found, though, was that for the libraries that did actually perform better on the functional and security side of things, there was a lot more documentation and code examples of peripheral features. So that's things like, how do you do secure key storage, or how do you do password-based key generation? And those peripheral features were actually the things that would make or break the security or secure use of a particular library. In fact, they found that the call signatures, the way that these libraries were being invoked, was generally secure, but the users, the developers that were going through these studies, were actually copy-pasting secure functional code, but they didn't have the knowledge or the skill to identify the danger, because often in those examples, those code examples, it would have insecure inputs to these libraries. So you can't rely on a developer identifying dangers, identifying sharp spots in your APIs, and you definitely can't rely on them to find secure alternatives as well. So if your library has this base level of features and functionality, but it requires inputs from other libraries or like things in the core language, you can't actually rely on your users to actually use those properly and know when to use them as well. So what this fundamentally means for us as library authors is that it is not possible to have too many code examples. It is just like, I cannot be clearer about this. Like, if you think that you have too many code examples in your cryptography libraries, you don't. You can just keep going. In fact, you should keep going. That will get the best secure outcomes for your end users, or your developers in this particular case. And it just reinforces the previous finding as well, that if devs can't find working code examples in your documentation, they will go to Stack Overflow and find a footgun. So having great code examples, huge impact on the overall security of delivered code by users. So the main thing that you can do here as an author is create and maintain an overabundance of secure code examples in your libraries. So like I said before, if you think that you have too many, you don't. Just keep going. The other thing that's really important to do is to identify inputs and dependencies that your users are implicitly relying on. So other language features or other libraries that they need to use to be able to use your library appropriately and correctly and securely. And when you identify what those things are, either provide secure wrappers for them in your library. So, if you're using a strongly typed language, wrap another type, for instance, with some extra security checks around it, right? And also document them exhaustively. So make sure that all of the code examples that you have on your website are secure. It doesn't even matter if you have a code example that has a comment above it that says, this is insecure code and you shouldn't use it. Developers will go and click it. They will just ignore the comment, and they will just copy the insecure code and they will run it, and it'll get a functional result, but it won't be secure. So it's critical that you have functional, secure code examples, and you have an absolute plethora of them. So the TLDR from this particular paper is that misuse resistance helps, but it ain't enough. Devs do crave code examples, and you need to provide them. All right, and as we wrap up with the research here, the last thing that's worth talking about is putting runtime warnings into your API for potentially insecure usage. So again, another paper from this group, and with a bunch of other researchers as well, actually, called Developers Deserve Security Warnings Too. And it talks about the effect of integrated security on cryptographic API misuse. And this is published back in 2018. And so the experiment in this particular study was that they had the Python devs that were assigned 3 tasks with the stub code, so the symmetric key generation, symmetric encryption, and key storage. And they were separated into 2 separate groups, whether they were using a control or a patch version of PyCrypto. And again, ask the same question, is your code actually secure? And when we say a patched version of PyCrypto, they just did some pretty basic sort of overloading of like the constructor, so that when you would instantiate a potentially insecure a cryptographic primitive that the library was exposing, it would print the standard out and create and it would make sure that it would, that when it did create it, that you knew that you were doing something potentially unsafe. And the results of this are really fascinating. So they found that for the control condition and the patch condition, the functional success was about the same, right? But they found that for the developers in the patch condition, that through these extra warnings, they almost had twice the level of producing a successful secure result as well as a functional result. So nearly twice the rate. And plus, they also self-assessed their solutions as being more secure when they were given a warning as well. They also rated the control and the patch versions equally usable. There was no negligible statistical difference between their ratings there. And so, yeah, the other really interesting finding from this particular study was that the developers who wrote code that triggered a warning were actually 15 times more likely to convert it to a secure solution. So just that simple prompting, like we were talking about at the very beginning of this talk, that is enough to be able to change the mindset and get developers actually building applications with your libraries in a secure and functional way. And they actually studied this. I'm not going to go into the depths of this other paper, but there was a follow-up study to that as well, that actually did like a participatory design study for like what those warnings were in those cryptographic APIs. And the TLDR, the thing you need to focus on is that when you provide errors or warnings, you want to provide a title message, color, the source code location where that particular problem was happening, a link to an external resource. You don't have to enumerate all the different security problems, just create a link off to documentation on your site saying, hey, if you get this particular error, this is the sort of thing that you need to think about. And the last bit is message classification here. So those are really, that's it. Like when you create these runtime errors, also like having a way for people to be able to suppress them as well is sort of useful. I'll talk about that in a second, actually. But just these 5 things alone, if you're able to surface those to developers as they are writing code, that will significantly increase the likelihood that they will deliver both functional and secure code to their end users by using your library. So the really fascinating thing from this is that as a library author is that you don't have to change your API's shape. You don't have to change the ergonomics of your API to actually increase the secure usage of it. So just omitting runtime warnings does significantly improve secure usage of your library without actually changing any of the parameters or what the interface is to your library. So if you can just look at what is being passed or what is being instantiated and you go, oh, we are providing this particular insecure function, but there are like lots of footguns with doing this. You should probably not do that. That does change the developer perception about whether they're developing and delivering secure code. And this tallies with what I started with, right? It's the psychology stupid. So that priming, that is the #1 way to actually improve the secure usage of your APIs. And it goes back to what they recommended, prime developers on the spot when they need it while they are coding. So the 2 things that you can do here as a library author is make your library emit warnings when you detect potentially insecure usage, and provide an obvious mechanism as well to be able to silence warnings. The reason for that second part, and just to be clear, I said obvious, not easy. Like you might have to, utter a certain incantation to be able to, as a developer using one of these libraries, to do the insecure thing. But you want to provide an obvious way to do it. It doesn't have to be easy for them. And often that's because there are organizational factors that are outside the control of the developers. Like they have to use an insecure Cypher suite because they are interfacing with some other third-party piece of software that they don't have any control over. So, you want to allow them to do the insecure thing, but they need to really work hard to be able to do that. So, TLDR, use the runtime warnings to prime developers about insecure usage during dev. So, the takeaways for the talk today. Developers don't really prioritize security. They focus on performance and functionality, not in that order. They focus on functionality and performance. And really, as a cryptographic API publisher, author, maintainer, you have to do a lot of the hard work for them upfront to be able to get them to produce code that is both functional and secure. You can help developers and people that are using your libraries by prioritize security by providing targeted warnings in your APIs, frictionless, misuse-resistant APIs that work and are secure, and copious secure code examples in your documentation. Can't emphasize that enough. Like, just keep going with the secure examples in your documentation. Most security bugs actually happen on the periphery of your cryptography library. It's inside your users' applications. There's a whole bunch of other really interesting research into that, which I'll link to in a moment. But it's all about doing the hard work to make it easy for your users to be able to use your library, to be able to get a functional, secure result. I'm Lindsay Homewood. Thank you very much for listening, and I'm really keen to hear what questions you have.
Okay there. Thank you, Lindsay. So we just looking. I don't see any questions there at the moment.
Give people a little bit of time. In fact, while people are thinking about the sort of things that they're going to ask, I've got a heap of other documentation and references to point you at. So I've got the slides published over here at cypherstash.com/Lindsay. If you're interested in the sort of stuff that we're doing, definitely come help us. We're trying to build next generation cryptography. But the references are over here. So this is all the APA citations. I've got links as well to all these papers in free and open access. So you don't need to sign up for anything. The other thing as well, this is additional reading in case you're super inspired by the talk and want to go learn more about it. There's this paper from 2011 as well that's really fantastic. It's an empirical study of vulnerabilities in cryptographic libraries. It builds upon that 2013 research that I covered at the very beginning of the talk. But yeah, there's a huge amount of really interesting research on this, and if you're passionate about it, I highly recommend you go and read it.
Okay, thank you. So with that, I think we can close a few minutes early. And oh no, I'm hearing there is one question. Okay, so what are some examples of the common mistakes made by developers in the use of the APIs?
Yeah, that's a great question. So if you're interested in learning about that, it's these two papers that you want to check out. So API blind spots. This original study was done with Java. The second study replicated with Python and Java. So often it's down to parsing insecure inputs, mostly copied from code examples. And what they were able to do in these particular studies was that they actually enumerate a whole bunch of different common insecure usages of these different libraries. It mostly comes down to the inputs, though, that the developers are passing to those libraries. So yeah, highly recommend you go check that out.
Okay, we have another one. The TLDRs are really useful. How would you evaluate docs are sufficient and you are not getting any more benefits?
Yeah, that's a really good question, because at the end of the day, all organizations have to economize. Like, we would love to be able to just sit and write documentation and code examples for the rest of our lives, but there is obviously a point of diminishing returns. My strong recommendation for that is actually usability testing with your users. Ideally, you could partner up with an academic institution, but if you've got some sort of product function, if you're in a commercial organization or you've got maintainers that have got that sort of responsibility, I highly recommend constructing tasks like the sort of things that were outlined in these papers to actually look at how people are using it. Using your libraries as well as the documentation that you are providing. I strongly recommend just doing the qualitative and quantitative research. The other thing as well that you can do is check out, look at, particularly if you're in the open source space, look at the GitHub code search, how people are actually using it there. Being able to reach out to the developers that originally wrote that code and find out how exactly they came to that point. At the end of the day, every organization is going to have to make a choice about where they economize and what that point of diminishing returns is. But have a think about that ahead of time rather than just doing it has to be the other thing as well, it has to be a constant, like, repetitive, maintainable pace and process. Like, as you ship new features and provide new functionality to your users, you're going to have to maintain all of the code examples that you've got. So it's also that classic thing of, like, having so many tests that eventually, like, the crushing weight of the tests actually stops you from being able to do delivery. So it's this interesting balance that you've got to find. So perhaps some of the heuristics that you might use to work out, what's an optimal amount of test coverage, that probably applies to what we're doing here with, like, code examples for your libraries.
Okay, and maybe the final one, because we are on at 16:30 now. Any advice on how to improve APIs when you need to also maintain compatibility?
Yeah, that's a really great question. I will be upfront and say I don't have any good answers for that. I think that providing, sort of using some of the earlier techniques that I talked about, actually the techniques towards the end about providing warnings and things like that, are a really important way to be able to do that. I would also argue that it's okay to break backwards in compatibility at certain points as well. But if you do that, it is vitally important that you create smooth upgrade paths to the newer version of whatever you're producing. So Google did that relatively successfully with Keyser and Tink. They got to a point where they actually got a whole bunch of the feedback from these particular studies and went, oh no, we really need to improve the usability here. So they actually just end-of-lifed Keyser entirely. I probably use that as an example about how to sort of encourage users to upgrade to the latest, greatest, most secure, most functional thing.
Okay, another question has popped up. Let's see if we can squeeze that one in. To what extent can static types help ensure secure API usage?
That is a great...
any papers that look at this aspect of API design?
Yes, I don't have that linked in here, but I'll find you in the chat after this. There is lots of research into that, and a lot of it is contradictory.
Okay.
So... yeah, static analysis, good, but I'll link you to the other stuff.
Perfect.
We can talk about it later.
Take all that on the post-talk chat, and definitely, Lindsay, have a look at the comments. It was quite active while you were talking. Thank you very much.
Thank you very much.